Hi and welcome. In this lesson, we will talk about compression. Compression in English means reduction. In computer science, it means resizing files or data. We need to resize files for two reasons: data storage or data transfer between networks. So here's a very simple basic example. We have an elephant that represents a big file, and we need that elephant to be transformed into a rat, which represents a smaller file, to go through a pipe. In that case, in computer science, it represents a medium, which can be wired or wireless medium. There are two main types of compression: lossy or lossless compression. Lossy compression is used with images and videos, and we cannot recover the original data after the compression. Lossless compression is used with text and programs or codes, and we can always recover the original data. Otherwise, we would lose all the meaningful information. So the concept behind lossless compression can be represented in the following simple example. Imagine that we have this series of letters or symbols. We have 4 C's, we have 3 A's, and two B's. So the idea is to use less symbols to represent the same data by counting the number of occurrence of each symbol and writing down the number next to the symbol. So by applying this in this example, we get the following new representation of the same data for C, 3A, and 2B. So instead of having 9 symbols to represent the data, now we have 6. And we are able to roll back to get the same original stream of data. We can also write a very small program in any language using loop and if statement to write a function that compresses data that looks like this. One of the most famous and common techniques for lossless compression is called run length encoding. And let's take a very quick example. So we have this stream of symbols or data, 27 bits of digits, and the encoding of this stream looks like this. We have 9 zeros, so we write 0 and then 9. We have 8 ones, 1 and then 8, in the following manner. We have 10 zeros, then we write 0 and then 10. But this is not what should be stored. What should be stored is the binary representation of this encoding. So the new stream should look like this. After converting every digit of every value, we have 15 bits now. And this is achieved by taking every value, every number, decimal number into its binary representation. So number 8 is 1, 0, 0, 0, and we leave the number 1 the same. Number 8 is 1, 0, 0, 1 by leaving 0 on the left side the same. 10 is 1, 0, 1, 0 and leaving the 0 on the left the same. So from 27 bits to 15 bits, and we are able to roll back to get the original stream by simply counting the number of repetition for every digit. And this is called decoding. Here's another example where run length encoding is not applicable. We have this original stream of data, and this is the encoding for it: 4 zeros, 3 ones, 4 zeros, and 6 ones. And by writing down the binary representation for each decimal number, 4, 3, 4, and 6, we get an even bigger stream, 20 bits. In this example, the compression was not successful. Thus, it's not always applicable. Lossy compression is used to reduce images and videos, but we are not able to roll back to the original data. So we have here a 650 by 650 image that was reduced to 300 by 300. And by looking at these regions here, we can see that the pixels in the smaller image appearing, while on the lossless image on the right side, cannot be seen. And also in this region also, we can notice the artifacts. Lossy compression works by taking the group of pixels in the original image, calculating the average, and then converting the value of this group of pixels into one single value that will be the value of the pixel in the smaller image. So let's take a look at this example. We have number 8, and this is the smaller size. We have less number of pixels, as you can see. So we will take this group of pixels, and we can calculate the average. And now we have one single value for these pixels together. Can write this value in as one value of for the next in the next image for this pixel, and we can keep doing this for the next group of pixels and converting them into one single value for the next pixel in the other smaller image. And by doing this, we can now have now a compressed representation or a version of the original image, but with a much more less fewer number of pixels. Here's another example where an image was compressed to a smaller size, and as you can see, the number on the right side represents the average that was calculated from the original image by taking the group of pixels and calculating the average. And the new values now represent the value of the new pixel in the smaller version. Thank you so much. I'll see you in the next one.